Good morning. Welcome back to the session this morning devoted to new science and the definition of the second. This morning we will speak of time, clocks. Our first speaker this morning is Professor Hidetoshi Katori from the University of Tokyo in Japan. Professor Katori is an eminent physicist. He's devised a way to manipulate atoms in an optical lattice regime to be able to interrogate them and get a radiation with an accuracy which is at the level of 10 to the minus 18. This development has allowed the construction of what we call today optical clocks, which are leading us towards the redefinition of the second. Professor Katori is an eminent physicist, he is a very good engineer, and he takes care of the application of precise metrology and of the social impact of his work. For that, he has been recognized by many awards in Japan and all over the world. So, welcome, Professor Katori, to our meeting today.
My great honor to be here to present our work at Tokyo. And so, I'm working at the university. So, my research driving force is just curiosity. In my case, to seek higher and higher precision. And at the same time, we are dreaming of some future realized with these accurate clocks. And this is the story of my presentation today. So, I will start from very old memory, 35 years ago, when I encountered optical lattice idea. So it was on the Shinkansen. I asked ChatGPT, draw this cartoon. So it was good old days when a very honored scientist, Bill Phillips, is the father of laser cooling technique. So student was asked to escort honored guest to somewhere. So in this case, he visited our lab in Tokyo in the beginning, and then he moves to Kyoto for workshop. It's called the Japan-US Seminar, supported by my supervisor, Fujio Shimizu. So then Bill and Chris was happily discussing new finding. It was this, localization of atom in a three-dimensional standing wave. They observed a very narrow spectrum, free from Doppler shift. This is a very important idea to make a good clock. So this, I have no idea, because 35 years ago, I was just a student starting the physics. But I learned the idea of lambdic confinement from their conversation. By confining atoms much smaller than the wavelengths, then Doppler shift disappear. And this leads to an optical lattice clock idea. So I have no idea at this point, but their discussion imprinted in my memory. Then, so this is my talk. In atomic clock, we rely on the constancy of fundamental constant and measure transition frequency as precise as possible. Then raise the frequency to atomic transition frequency. Long coherence time of atom gives narrow spectrum, less than Hertz. But when I started, it was around 1990. Then quantum noise was a problem by observing singly trapped ion. So we thought many atoms helps to reduce, precisely determine the center frequency, which is proportional to square root of n. And this is the very beginning of the lattice clock idea. The important trick that we made is the so-called right shift cancellation, which is to adjust the dipole polarizability in the ground state and upper state, so that we can eliminate the right shift perturbations caused by the optical lattice. The good point is that this protocol is only given by the frequency. Frequency is the most accurately measurable quantity. Therefore, this protocol works very well. So we proposed optical lattice clock idea in 2001. We aimed at the excellent stability by increasing the number of atoms. The key is the engineered right shift trap, defined by frequency. In 2014, we realized 2 times 10 to the minus 14 level agreement between two clocks by reducing black-body radiation shift, which is a bit difficult topic to discuss here. And then we started to lab-sized clock like this, to transportable. We hope to make use of these clocks for the space-time sensing. In 2018, we packed these lab clocks into 2 black boxes. This is clock 1 and 2. It's a physics package. We have laser-cooled atoms trapped in the lattice. Then we demonstrated by lifting up one of the clock. Then you will see upper clock ticks faster. Seeing is believing. This way. We uplift one of the clock. Then we compare clock frequency between the two. In the beginning, when we set the clock at the same height, the frequency is exactly the same at the level of 10 to the minus 18. But if you lift up one of the clock by 1 meter, then you will find that the upper clock ticks faster by 47 millihertz in this case. This is caused by a gravitational redshift. On Earth, gravitational redshift is given by this, given by the gravitational potential difference between the clocks. It corresponds to 1 times 10 to the minus 18 per every centimeter. So if you have accurate clock, then the two clocks will resolve 1 centimeter height difference. Then it's like Dali's melting clock in reality. This is a new application of the clocks in the future. So we are now routinely reading 18th digits of strontium pendulum. Strontium oscillates at 429 terahertz. And it should be like this. And up to 16 digits, we can describe based on SI second. But beyond that, we have no words to express that frequency. Because we are observing, but there is no way. This is a crisis in science. So this motivates the redefinition of a second. And they planned the redefinition 2030, and new candidate may be decided in next year. I don't know. So this is a discussion today. So why atomic clocks? Because of curiosity. We want to explore extreme precision. So according to Arthur Shallow, that never measure anything but frequency, then very important tool to measure is a very accurate atomic clock. And optical lattice clock protocol also rely on this word, define the protocol by frequency. So we show our clock comparison so far. Then clock is a tool to measure space-time. We can test the relativity, and we can use the relativity. And then we will address our next challenge for optical lattice clock. And in the last part of the talk, I will introduce our collaboration with industry partners. We are transferring our technology to industry, and they realize it and commercialize it, and they will start new age for the clocks. This is what's inside in the first generation transportable clock. This is easy to understand. We have strontium source, and strontium goes this way, and we shine laser to decelerate it. Finally, we shine lasers three-dimensionally and confine the atom to an optical lattice. We made optical lattice inside this bow tie cavity. This is why we want to move atoms from the trapping position to a so-called blackbody radiation shield. This is an important trick to protect atom from a thermal radiation field. We feel warm here. This is because of the blackbody radiation. The electric field amplitude is like 8 volts per centimeter. It's a good amount of electric field. And atoms can be shifted by these electric fields. So we shuttle the atom to the blackbody radiation shield, and then we perform spectroscopy there. In the beginning, we demonstrated these clocks at the Tokyo Skytree, which is a broadcasting tower in Tokyo, using 450-meter high difference. We demonstrated a gravitational redshift test. We measured the frequency difference by setting at the ground floor and of the battery floor. And we saw 20 Hz frequency shift. And we checked if this agrees with the gravitational difference between the clocks. We accurately measure the height difference between the clocks, and we determined that deviation is less than 10 to the minus 5. This is very competitive to the space experiment for the clocks. The important message of this demonstration is that this kind of high-performance clocks can be usable outside the laboratory. So it's a practical device already. So by using clocks, we can perform chronometric leveling. If you compare two clocks and read the frequency difference between the clocks, as I said in the beginning, we can tell the height difference between the two clocks at the centimeter resolution, which is an important role for the clock in the next stage. So we are now demonstrating these works. we have 2 clocks at Riken, which is next to Tokyo, and we put our 3rd clock at the Misawa Observatory. Some reason we took our clock to Misawa Observatory is that 15 or 14 years ago, we had a big earthquake there. It's called the Tohoku earthquake. And the ground level was subsided by 30 centimeters. And now it's gradually uplifted every 3 centimeters per year. So if you have an accurate clock, then we can observe this kind of ground deformation by clocks. And another topic we are fighting with is to see tidal effect between the 2 clocks. Because of 500-kilometer distance, there is a slight difference in the tidal phase. Then the amplitude can be as much as 5 centimeters over 6 hours. This can be an interesting thing to see. And the message is that the Earth is no longer a solid reference frame for accurate clocks. Instead, clock can be a novel tool for geology. This is what we are doing. We have 2 clocks at Riken and 1 clock at Misawa Observatory. And this is a random deviation for the clock comparison. This starts from 10 to the minus 16 and go down to low 10 to the minus 18 in an average time of 3 hours. And this is a measurement. So this corresponds to 3 hours. And blue one is what we measured between the 2 clocks, 500 kilometers away. And red one is a prediction of a tidal effect. I don't say that we are observing tidal effect. We need more noise hunting to the goal, but we are very close to that goal. So the next demonstration was the transportability of our clock. In 2023, we packed our clock in a wooden box, and the clock flies. The clock flies to NPL. And NPL hosted our clock there, and then we went to PTB to compare. And this is the result of the comparison. The agreement is not at the level of 10 to the minus 18, but it's around 3 times 10 to the minus 17. So this is the very first step for the future agreement of the clock. And more comparisons and feedback required. And the message from this comparison is that with a single clock at hand, it's hard to find subtle experimental failure at 10 to the minus 18 level. So reference clocks will significantly accelerate the troubleshooting. This is our feeling working in my lab. So in 2001, we thought about optical lattice clock idea. The idea is to tune the lattice trap potential to be the same by frequency and trap many atoms to reduce quantum projection noise. And now we need next idea to further improve this clock. So we want to explore uninvestigated stability and precision. In the era of cesium clock, it would take almost a day to achieve 10 to the minus 15, and hundreds of years to achieve 10 to the minus 18. So it's almost impossible experiment to achieve 10 to the minus 18. But with the invention of single ion clock, it can be realizable because 10 days is long, but not a bad averaging time. In the beginning, we envisioned to achieve 10 to the minus 18 in a second. This is why we can observe millions of atoms at a time. So we can speed up millions of time. But the thing is that then the laser matters. Because of the finite laser line width, this start point is determined. By employing better lasers, such as cryogenic silicon cavity, as done by Zidler and PTB, you can improve this starting point. But we want to make compact clock. For that purpose, we want to still start from this region. And now we are thinking about strontium beam clock. With that idea, I expect we can improve the uncertainty inversely proportional to the averaging time until it hits the quantum projection noise limit. So the idea is that in the conventional atomic clock, we repeated many experiments, many frequency measurements, and averaged it. This is why stability improves as square root of tau. But if you continuously monitor the laser frequency, then stability would improve inverse of time. To realize that idea, we are now building a new machine. It's a continuous cooling scheme and continuous rolling into a moving lattice and continuous spectroscopy. Very recently, we succeeded the first step. We prepared cold atoms and guided them in a magnetic guide, and finally, we obtained a very cold atom in the end. Then we transferred the atom to the moving lattice and moves in this way. And we shine clock laser from here. And in this permalloy chamber, we apply a magnetic field. And this magnetic field opens forbidden transition. This is called magnetic induced spectroscopy. With that, atoms rapidly oscillate. Ground state, excited state, ground state again, in this way, in this spectroscopy chamber. And if you observe the atom here, then you can continuously measure atomic spectrum. This is the idea. So, for the first step, we measured this spatial distribution of atoms inside this spectroscopy chamber. This is it. We pull the atom outside the chamber, and we measure the population of atoms. And this way, this is atoms on a moving lattice, and this bright and dark corresponds to atomic state, ground excited, ground excited. So this is experimental data. So we observe a clear Rabi oscillation in a continuous manner. So this is the first step for the continuous clock we are hoping. So in the last part, I will introduce our collaboration with industry. Our fun is to think about new ideas for experiment and new technologies. And we, in collaboration with industry partner, which is Shimazu, and JEO, and NTT, which is a telecom company, and they commercialize it or networking the clocks. And in collaboration with geophysicists or people in the space agency, they will think about the future applications of clocks. We started this project in 2018. So we are constructing clocks with company people. And finally, we did it. We packed whole clock inside this box. The total volume is 250 liters. And weight is a bit heavy, 200 kilograms per consumption, 700 watts. And this is commercially available and started taking order 2 months ago. So we compared this clock with our clock. This is the result. Stability goes down to, say, mid-90 region in 3 hours of averaging time. And this is the measurement of between the clocks. It's within 4 times 10 to the minus 18. It's a stated systematic uncertainty. And the agreement is 2 times 10 to the minus 18. So this is a press release they did 2 months ago. It's in Japanese. But interestingly, this is March 6th. But the French press was earlier. This is it. AFP reported this news on March 5th. It's 1 day earlier. So this kind of news is available in a translation worldwide. So with these commercial clocks, we can think of networks of clocks, many clocks. Our idea for clock is that clocks should be synchronized. So our mind is still living in the absolute time in Newtonian mechanics. But if you have an accurate atomic clock, this clock can lose less than 30 picoseconds per year. So synchronization is not necessary for normal purpose. And these kind of standard clock, we will see this kind of curved space-time given by gravity. Upper clock ticks faster, slower clock ticks slower, and moving clock ticks slower, for example. And this is exactly the Darius clock. So let's say, go for a drive with optical lattice clock. We started weekend at t equals 0. And if you drive highway at 100 kilometers per hour, then clock delays. And if you climb up the mountain, then they advance and go back to weekend again. So my clock advanced by 600 picoseconds. So that my colleague in weekend looked a bit younger. So making clock was a kind of national strategy. Cesium clock was invented in 1955, and it was an amazing strategy of United States that they launched by GPS and make a network of clocks. Once they are used by a civilian purpose, then Google Maps changed the world. Now, no escort is necessary to go somewhere. And then automatic driving is reality. We can think of a similar story for high-performance clock. We proposed this clock 20 years ago, and now it's commercialized. And the definition of the second may push this further. Then we can think of a relativistic space-time platform business with these clocks. So we need to think about strategies for implementing ensemble of clocks in society. The most important challenge for us now is that to find target that only optical clocks can access. So there is a wide application for conventional clocks. And because we have better accuracy, then we can replace some of the application. But there should be a wide field that only optical clock can see. So clock leveling is one of the applications, but this is just one of the applications. We need to find this large field. It's almost time, so I will skip. So I think the important thing is to attract interest outside metrology community. So we have a happy collaboration with industry. This is because optical lattice clocks are no longer clocks. They can be quantum sensors for space-time. And if you manipulate single atom, it's a basis for neutral atom-based quantum computer. So industry are happy to work with us. So we can harness the power of industry for future clocks and accelerate the definition. And this is the final slide. So we hope to passing the baton to the next generation. So I was asked to contribute to the final chapter for the high school physics textbook. And I gave them the picture I thought about. If you have a network of clocks, there will be a good sensor for what's happening underground. For example, if the volcano is about to erupt, then there is a small uplift of the hill, and this can be measured by clocks, for example. So, optical clock, lattice clock demonstrate there is melting clock that see the curved spacetime on a personal scale. We want to change the rules of the game, conventional idea for the making clocks. And we want to approach unexplored precision. And important thing is envision an expected future with these clocks. There are large, untouched area in science or business, which is combination of quantum and gravity. Thank you very much for your attention.
Thank you, Professor Katori, for this inspiring talk. And I know there will be questions probably. Keep your question for the end of the session. We have a next speaker, who is Dr. Marina Gersholz from the National Research Council of Canada. Marina was the head of the Time and Frequency Department for several years, and she has been very active in the international activity. In the Consultative Committee for Time and Frequency, we have a task force for a definition of the second, and Marina was chairing one of the subgroups. She was also chairing the working group on the International Atomic Time, and she has been helping in our program for capacity building related to time and frequency. And yes, I said she was, because Marina 2 months ago left the time and frequency community and started a new job as director of a program on quantum sensors at the National Research Council. But she has been so kind to maintain her engagement with us today. And so, Marina, please come to the stage to talk about the CCCTF roadmap to the definition of the second.
Hello, everyone. It's a great pleasure for me to present the work of Time and Frequency, Consultative Committee on Time and Frequency community as a whole towards the redefinition of the second. And thank you, Patricia, for the very kind introduction. So SI second is the most important unit of the SI system. Why? Because since 2019, when the redefinition of all the units, almost all the units moved to the relevant fundamental constants, you can see now that the definition of all the units, with the exception of mole, directly depends on the unit of SI second. You can see the yellow-colored segment of the inner circle of the SI wheels. So for that reason, because all SI system depends on SI second, all measurements depend on the second, the whole world depends on the SI second. The redefinition of the SI second is a critical process that will impact many different communities, not just the National Metrology Institutes, but the industry and the public and the wide applications. So we have to take a very good care of the second and of its redefinition. So just a bit of history. When in 1960 the SI system was established, the second, the unit of time, was defined through astronomical observations as a fraction of a tropical year. Then already in 1967, when the high-resolution spectroscopy of cesium atoms showed that they provided a much more stable and accurate realization of frequency measurements, there was a change in the definition of a second that now became an atomic time. So a specific transition in a cesium atom was used to define a second. And one important advancement from astronomical time to atomic time is the duration of one period of this repeatable measurement of time. So in astronomical time, tropical year is the unit of measurement, so you have to wait a whole year to repeat your measurement. With atomic systems, you can have almost 10 billion measurements in 1 second of the frequency. So that was an improvement. In the CGPM resolution from 2018, the wording of the definition was changed to become similar to the wording of other units that were redefined at that time with the physical constants, but the substance of the definition didn't change. So we still have cesium as the reference for the definition of the second. Now let's look at this graph. You have seen this before, you probably have seen this multiple times. This presents the evolution of accuracy in the development of atomic clocks. And the blue squares, they show the advancement and the accuracy of the microwave cesium clocks. And you can see on this graph, one vertical division represents 2 orders of magnitude improvement in the accuracy. And every horizontal division is a decade. You can see that microwave clocks were improving steadily. I can see 2 orders of magnitude per decade with a qualitative jump when fountain cesium clocks were developed, which improved the accuracy 2 orders of magnitude. But we can see that cesium clocks have reached the limit of the accuracy. The red circles represent optical clocks. And when optical clocks first started, they were not as good as cesium clocks. But you can see that the progress in the accuracy of the optical clocks progressed very fast, almost a vertical line. And it continues to this day. It slowed down a little bit, but it's still going down. You can see here we are in the 10 to minus 18 and 10 to minus 19 regime already. One of the reasons that optical clocks allow us to have much better accuracy in the realization of the second and the frequency measurements is because the clock transition has higher frequency. Remember when I told you when we moved from astronomical time to atomic time, the clock transition frequency changed from 1 year period to 10 gigahertz of frequency, which is many orders of magnitude shorter. The same with the transition from microwave clocks to optical clocks. Here, just on the, we see here the energy level diagrams for cesium atom with the clock transition at 9 gigahertz, and an example of one of the optical clock. This is a strontium ion clock transition, which is at 700 almost nanometers. So just by this change alone, without considering other advantages of going from cesium clocks to optical clocks, we can see a potential improvement of 5 orders of magnitude in the resolution. So we go again to this diagram that I showed you, to the advancement of optical clock performance over the years, and we can see that already in 2007 approximately here, the accuracy of the optical clock surpassed that of the microwave clocks. That's why the circles that sit below the cesium blue squares, they're marked in light red and pink color rather than dark red color. And this is because we cannot measure anything better than the SI second definition allows us. And when the evaluated frequency of optical clocks is at the 10 to minus 17, 18, and 19 level now, we still cannot measure it because the cesium best measurements are only at the 10 to minus 16 level. So we have a ruler that is not doesn't have the divisions that precise enough for our needs anymore. So the redefinition has been needed since that time. Then, 10 years later, so it took quite a while, the first roadmap towards the redefinition of the second was published by the CCTF. It was presented at the CCTF meeting, and you can see there are several conditions listed on this roadmap that address the requirements of what needs to be accomplished for the redefinition to go ahead. So there are requirements on the accuracy of the clocks, the frequency ratio measurements, stability, contribution to the TAI, etc. And the CCTF community started to work with a lot of effort and many people hours involvement in working on this roadmap. So in 2020, a more detailed roadmap was prepared. This one specified the conditions for the redefinition, grouping them into 3 different topics, and also dividing the requirements into mandatory and desirable criteria. That I'm showing the first group, first theme of conditions on the slide. The top red boxes are the mandatory criteria that has to be met for us to go ahead with the redefinition, and the blue ones are desirable criteria. And you can see that this theme, for example, it addresses the frequency standards and the TI. So it lists again the measurement, the number of measurements that have to be done, and what should be the uncertainties of these measurements. And it lists these conditions with greater detail than the first roadmap. For example, it specifies that the measurements need to be done at different laboratories, for example, to make sure there are no systematic effects in the results. Another group of criteria is related to time and frequency comparisons and dissemination. Because the SI second, the new redefined SI second, should be available to multiple users. It should be accessible to multiple users. It should not degrade the performance of the TI time scale, and it should be long-lasting. So that's why we have so much criteria. There is also a third group that is acceptance criteria of the new definition, and this is what I told you about, that commercial devices should be developed, and everybody should have access to the new definition. So the things looked really well for our progress towards the redefinition of the second, such that in 2022, CGPM issued a resolution that accepted the roadmap and expected the proposals for the new definition of the second to be adopted in 2026 at the CGPM meeting, with the new second definition coming into effect in 2030. So 2026 is already next year. The time flies. So we're going back to this graph. I like it a lot. So we identified the time when the first measurements demonstrated that optical clocks are indeed can be built and can be measured with higher accuracy than cesium microwave clocks. So the new definition is needed since 2007. Just quick reminder. So when the SI second was established, when the SI system was established in 1960, the second was astronomical. Then just in 7 years, the new atomic second was already adopted and realized. It took only 7 years to shift to a completely new way of measuring frequency. Nowadays, we go in much slower. So the roadmap first created only 10 years after the initial measurements surpassed the accuracy of the microwave clocks. And that roadmap proposed that the decision for how the second should be redefined happens in 2026. which is almost 20 years since the first measurements, when the new second taking the redefinition taking place and the new second going into effect in 2030. So we're progressing much slower. We're being more careful for the reasons that I already mentioned before. We want to make sure that this new second will be best choice for scientific and technological basis, and also it will be long-lasting and will make the best choice. Is it easy? One of the reasons is why it takes so long is because we have a lot of optical clocks. So the graph that I showed you before on the progress of the optical clocks development, the red circles, these are all different varieties of optical clocks. Here is a list and some images that I grabbed on the internet of the clocks from different National Metrology Institutes. This is an incomplete list, and it shows the clocks, some of the clocks that different laboratories are developing and looking at. You can see the common trait is that the clock transition for all of them is in the optical domain, from 200 nanometers to 700 nanometers. And these clocks have different characteristics. They have different advantages. Some can be more accurate. Some are easier to construct. Some have laser frequencies that are required that are more easily accessible. Many different considerations for which clock to pick. The species that I showed you, so we call them species, and the clocks are developed in different labs around the world. Some bigger labs have different species of clocks, and they can make frequency ratio measurements and do analysis, study the performance of their clocks and different systematic effects when they have multiple clocks being developed. Some other smaller institutes focus all their efforts on their favorite species, and maybe that's why they're more attached to their favorite species and think this is the best option for the redefinition. So many labs have clocks right now. Again, that map was an incomplete list. So the Consultative Committee on Time and Frequency organized a task force to work on the redefinition. I showed you the criteria that was developed by this task force, but the task force actually has 3 subgroups. The first group is options subgroup. The second is criteria subgroup, and the third is education. I'll speak a little about these 3 subgroups. The important point I want to highlight on this slide is there are members in the subgroups that come from all different laboratories and from all different regional metrology organizations, because we want to make sure that the redefinition is universal. It works for everybody. So the first group on options, their task is identify the options for the redefinition, analyze the pros and cons, and make proposals for the best choice of the redefinition. The second group is looking at the criteria. I showed you 3 slides worth with many, many boxes dedicated to different criteria. And so the second subgroup is monitoring the fulfillment level of this criteria and identifies areas that require improvement, and focus provides recommendations. And the third group is on education and communication, is to make the work on the redefinition better known to the public, prepare the public, the scientific community and the general public for the redefinition. And what I'm doing right now falls under that subgroup activity. So what are the 3 options? I'll start with option number 3. The option number 3 would have been ideal because it would be the same type of the definition as all other SI units are defined right now. It would be based on fixing a value of a relevant fundamental constant. Unfortunately, such as the mass of the electron, for example. Unfortunately, no fundamental constant at present is known with sufficient accuracy not to degrade the quality of the SI second realization. So option 3 is impractical at at the moment. We're not looking at it because we want to improve the definition of the second, not to degrade it. So option 1 is an option when we just pick a different species and base the definition on a specific transition of that species. That's an easy choice, except that we have too many species to pick from. But the definition would be similar to the one we have right now with cesium. Option number 2 is to actually recognize the fact that we have many different clocks that have competitive performance characteristics. And so this option 2 would be based on an ensemble average geometric mean of frequencies of different clocks, and the weights in this ensemble will be determined by the uncertainties of each individual realization. Now, option 2 has 2 flavors. One flavor, 2A, is when we fix the list of species that we will be using for the redefinition of the second, and this will be fixed and identified by CGPM resolution. And the option 2B is also an ensemble of species, but this ensemble is allowed to change, and the species can come on this ensemble. The weight of the species can change as the knowledge of their frequencies changes. This redefinition will be more long-lasting because it will be similar to changing the recommended frequency values for frequency standards, and the value will advance as we realize the second better and better with new clocks coming on board, more precision measurement. So there are pros and cons for each of the options. We already discussed the option number 3, fixing a fundamental constant. Unfortunately, this will cause 4 orders of magnitude reduction in the accuracy impractical. Option number 1, when we pick one species, it's very familiar and practical. It can immediately provide us with 2 orders of magnitude improvement in accuracy, because there are several clocks that achieve 10 to minus 18 level right now, but it's hard to find a consensus. And another risk is that with a different clock becoming more accurate in the near future, we will very soon require a new definition. And you've seen how long it takes, how much work is required. We don't want really to go through redefinition process again and too soon. The option number 2, that is an ensemble of species, it also promises an improvement of 2 orders of magnitude in accuracy of the definition. It's a flexible scheme, but it's a completely different approach than all other SI units. It's a completely different approach to the spirit of the SI system and conceptual deviation. And this presents difficulty for many metrologists to accept. So if you want to read more about the details of the technical background on how this redefinition process is advancing, more details on pros and cons, there is an open access article published by the task force that you can find online. So I told you about criteria. We have mandatory criteria, and the subgroup and criteria is monitoring the advancement of each of that criteria and creates this nice charts, colorful charts for each one of them. This is the chart for 2022. And you can see that we have a few criteria that sit nicely in the green zone. This is where we need to be for the redefinition. But we still have significant number of criteria that are deep in the red. So clearly the work needs to advance on this front. The criteria looks at realization of individual clocks, and just here I'm showing you, for example, the fact sheet documents that are prepared by the task force that describe different species and their published uncertainty levels. On this graph that you can access on the BIPM website, the contributions of different clocks to the TI calculations are presented with different colored dots, and we are interested in the blue dots at the top because these are all optical clocks. And you can see that there are some contributions of these clocks, but if we compare the situation in 2022 and 2024, we can see that there were more clocks contributing in 1 month in 22 than there are now right now. And we need solid lines of blue color on this graph to have continuously running and clocks that report regularly to BIPM for the TI calculation. There's been a lot of advancement in time and frequency comparison research and systems being built. I'm just showing here different frequency links that connect countries in Europe that have free space frequency comparisons. In Japan, you saw some results in the previous talk. So that allows us to fulfill the criteria on frequency ratio measurements. But we need to publish more results as a community. Also, the development of transportable clocks is very important because we need to compare clocks between different continents. At present, we don't have technology that allows comparison of clocks at these distances. So transportable clocks will not only allow the dissemination of the second to different locations on Earth, but they also will bring the technology to a much higher readiness level, higher uptimes, and more frequent contribution to TAI, which is required for the redefinition. So because of this frequency comparison methods being developed recently in recent years, you can see that there's been a progress in one of the criteria, regular contributions to TI, availability of sustainable technologies for FS comparisons. So that rhombus has moved forward, but the other ones are still behind. So clearly a lot of effort is required urgently to fulfill the criteria. The task force also tries to promote the information about the redefinition through BIPM website. We created a list of frequently asked questions, which I invite you all to access. They provide the information on some basic questions, but also on some more obscure ones. What happens if we picked a species and discovered that there was a systematic effect that we didn't account for? So what will happen at that situation? So we try to prepare answers for that. We have technical exchanges. We have meetings. You can see the numbers are very high. The community is working very hard on the redefinition process, on making sure that we get ready for the redefinition. But the questions still remain. Which option should we go with? Option 1 or option 2? So single species or ensemble of species. If we go with ensemble of species, should it be option 2A or 2B? Fixed list or flexible list? Which species do we pick and when? Because the question of when is also important. You saw the fulfillment criteria is not, the fulfillment level of different criteria is not yet in the green zone. So we have this timeline that you see here. We're sitting very close to the decision-making point, and with the help of the community, we'll have to decide very quickly what's our next step is. And this is my concluding slide. While we are preparing for the redefinition using optical clocks, new clocks with potential for even higher accuracy are already been, well, they have been studied for many years, but recently they demonstrated results that bring them much, much closer to actual clock performance and realization. These are nuclear clocks, and I grabbed a few key publications on the topic from several groups. So we have to move fast, or then we will have a different redefinition on our hands. And with that, I close, and thank you very much for your attention.
Thank you, Marina, for your talk and for your information, and also to give us motivation to progress in our job at the CCTF. So now it is time for the panel discussion, The panel will be formed by our two speakers and by other panelists that I will introduce. The first one is Professor Bill Phillips from the National Institute of Standard and Technology in the United States. Shall I introduce Professor Bill Phillips? She got the Nobel Prize in 1997 related to his work in laser cooling of atoms. This is the capacity to manipulate atoms with lasers to be able to slow them down and put them in the best condition to get a radiation out of them, which is so precise, so accurate to build atomic clock. And the current cesium photon are based on this principle, and this is why Professor Bill Phillips is so important in our community. But he is also a great friend of us, and he is always enthusiastic to speak about metrology, clocks, and interaction of atom and lasers. And so we are very happy to have him here today and to listen to him again as we had the pleasure on Monday. So welcome Professor Bill Phillips to our panel. And then the panel will be coordinated by Professor Noël Dimarque, who is the president of the Consultative Committee for Time and Frequency. Noël is professor in the Université de Côte d'Azur in France, but before he was the head of the French Institution for Time and Frequency Metrology, and he is now also the president of the Bureau de Longitude, taking care of time and space for the international community. Noël is guiding the Consultative Committee for Time and Frequency since 2019, and he has been very attentive and very engaged in the development of the hot topics for the CCTF, one of which is the redefinition of the second. Please, Noël.
Good morning, ladies and gentlemen. Thanks, Patricia, for this very kind introduction. So I'm really happy and honored to be the moderator of this panel discussion with so outstanding panelists. I would like to give some introductive remarks before entering the discussion. As Marina pointed out, of course, we are modest, but let us say that the second is the most important unit, not only because it has been always realized with the lowest uncertainty by far compared to the other units, but also, and it has been shown since 2018 and the revised SI, the second is above the other units, since all the basis units, SI units, are now linked to the second, except the mole. And the nice medal that was given to us yesterday is a nice illustration of this special position of the second in the SI system. But the second has also, and the unit of time has also a lot of specificities with respect to the other units. This is a unit that you must measure continuously without dead time, and so it's very important for the organization and the operation in the labs and at the international level. It is also a special unit. Yesterday we heard about quantum technology for and with metrology, and of course we know that since decades the definition of time relies on quantum properties of matter and on quantum technologies. And also it is a very specific unit because, to my knowledge, it's the only unit that you can distribute, disseminate, broadcast by radio, microwave signals, or by optical signals through optical fibers. And so it is a specific organization of our community, and it allows to have access to the realization of the definition either directly from a signal provided by the primary standards or also via UTC, since this timescale, the rate of this kind of timescale is provide the SI unit of time the second. And talking about UTC, I think it's a good opportunity to thank BIPM and the time department of BIPM for the outstanding work that has been and that is carried out to ensure the continuous construction and the dissemination of UTC. And here we can say really it is a construction and dissemination for all times and all peoples. And we are convinced that this mission of BIPM will be pursued in the next 150 years, not only for UTC and as a reference time for the Earth, but also for the Moon reference time, for the next future lunar mission in the coming soon, and then after also for Mars reference time. So you have seen with Marina presentation that CCTF is working very hard on the roadmap towards the redefinition of the second. You have seen that there are still some open questions and issues we have to solve urgently. This work is really a collective work, and it's important to get the maximum questions, remarks, feedback on the different aspects that has been presented this morning. These different aspects of the redefinition. So we have many questions to address, and the panel discussion with such outstanding panelists is a good occasion to do so. So to optimize the interaction with the audience, I will ask only one question. Don't worry, I have many other questions to ask, but I will ask only one question, and then we will move rapidly to exchanges with the audience in the room. And so please prepare your question, because it's a good occasion to do so. So, to ask the first, I stay here for the first question, and then I will come with you. The first question, it has been addressed in the different presentation on Tuesday by Bill and this morning by Hidetoshi. Which specific advancement and progress do you expect in the future with the new definition and with the use of optical frequency standards? What kind of new application, new ideas can be stimulated with optical frequency standards and the new definition? Because as it has been shown this morning, optical frequency standards can be seen either as reference for frequency and time, but they also can be seen as sensors, space-time sensors. So you see that there are applications not only for science aspects, but also for society aspects in these two domains. So this is the first question. And Bill, if you want to start the discussion, thank you.
Well, let me begin my answer by recalling what Professor Katori said about being in a university and doing curiosity-driven research. I am at a government agency, a mission agency. We have a very specific mission, and we're interested in exactly the same things. So I think that's an important lesson about the things that motivate us in research, that very often what appear to be very different motivations can lead us to exactly the same kind of research. And the thing I'm most excited about is very much a curiosity-driven idea. I want these incredibly accurate and increasingly accurate clocks in situations where we can have two clocks of very different atoms. Atoms where the transition frequency depends upon the fine structure constant in very different ways. And it's not very hard to find great transitions where great transitions meaning transitions that have very narrow intrinsic line widths and, well, hopefully very little sensitivity to light shifts and black body radiation, which we haven't really talked about very much, but maybe as the panel progresses, we'll get into why these are important issues in making decisions about what the best clocks are going to be. But we can find multiple transitions. This is one of the problems in deciding which transition to have. But it's a great thing to have these multiple transitions because they depend on the fine structure constant differently, or other constants. And what I want to do is experiments where you put two of these clocks together and move them in the gravitational potential. The ideal thing would be to have a satellite with a very elliptical orbit, either around the Earth or around the Sun, and look at the ratio between these two clocks as the satellite's orbit progresses. If Einstein is right, and Einstein has been annoyingly right about these things, but if Einstein is right, the ratio shouldn't change. And so far, that's been the case in all the measurements that we've made. But we know, or we hope, that somehow we're going to find some kind of a failure of Einstein's theory of general relativity, because we have a real hard problem reconciling Einstein's theory of gravity with the theory of quantum mechanics. Both of these theories predict essentially perfectly everything we observe, but they're inconsistent with each other, and one of the great challenges of modern physics is how do we resolve that inconsistency? Well, if we could find a failure of Einstein's theory because of these wonderfully accurate clocks, then this might give us a clue as to where to look to be able to reconcile quantum mechanics and gravity. So this is the thing that's really exciting me about the possibility of using optical frequency standards in the future.
Thanks, Bill, for that. Marina, do you want to add?
I would like to add that in addition to scientific curiosity and exciting new physics we may discover, there are also a lot of potential for technology development, with optical clocks becoming smaller and more accessible, with the technologies for transferring frequency and time synchronization over long distances. I'm sure new applications will come on board, the same as Professor Katori showed with GPS technology, that we probably didn't envision all the applications we use it for right now. I believe that with better time precision, we will have new things to enjoy. One of the immediate applications that comes to mind is communication, quantum communication, the quantum entanglement that requires very high level of synchronization and clock references. So maybe that will become more prevalent when the clocks are available. Thank you.
Thanks, Marina. Hidetoshi.
Yeah, so the definition will be very important to describe the measurement outcome as number and exchange that number by paper journals. This is a very basic of the science, measure and compare with the other. And as for the Bill's measurement, so scientists don't require the redefinition. Scientists just measure the ratio between the clocks. This is a practical way for the scientists. But if there is a definition, and we can describe that kind of very accurate measurement by number and exchange it by written material, that's a wonderful thing.
Just before a question from the audience, just in the same spirit of the new ideas and new challenges that can be faced with the next optical frequency standard. On one hand, we plan to define the unit of time on a frequency or an ensemble of frequencies from different species. And on the other hand, we use the same optical frequency standard to test general fundamental physics, and especially to test the constancy of the fundamental constant. So do you see any kind of a contradiction between the philosophy to rely on fundamental constant and at the same time searching a drift, variation in space and time of fundamental constant? I don't know, Bill or...
Well, yeah, this is something that is a favorite topic of mine. As you indicate, these wonderfully accurate clocks can allow us to, in addition to the experiment I described, to ask, is the fine structure constant changing in time? Now, you ask a very important question. We use fundamental constants like the speed of light, Planck's constant, to define things like the meter and the kilogram. So what if those constants change? What's the deal? Those constants cannot change. It would be illegal for those constants to change. And I think it's really important to understand this point, that if we can define a constant, that means that it's a human construct, that it's a construct that we've decided what the value is in order to decide what we mean by a meter or what we mean by a second or a kilogram. That's something we can decide. We cannot decide the value of dimensionless or unitless constants like the fine structure constant, or, for example, the ratio of the mass of the electron and the proton. These are dimensionless or unitless constants, and they're defined by the way nature is. It's not something we get to decide. So they're very different kinds of things. Now, I should say, not everyone agrees. There are scientists who, in all other respects, seem to be reasonably intelligent, who who say that it's actually meaningful to talk about a change in time of something like the speed of light. These people are wrong. And but I should point out that not everyone agrees with what I've just said. But apparently, judging from the reaction of the panel, everyone on this panel agrees with what I just said.
Do you agree, Marina Hitedoshi? You can react.
I agree completely, but I think what's important to do the studies is to have a different species, so we will be able to compare them in the future, and it's important that even if a single transition is chosen as the new definition, that the research into different types of clock continues to allow us the studies of the fundamental constants changes.
And that study into different kinds of species is absolutely important, that continue regardless of which of the options we choose.
Yeah, exactly. So there are two aspects. I said in the beginning, we rely on the constancy of fundamental constant, but we are working on precise atomic clocks to explore if it is constant or not. That was the real motivation for me to start working. But to appeal the usefulness of this kind of atomic clock to a general audience or real user, we need to say it's constant. So there are two aspects. That's an interesting thing. Borrow the power of the industry, make good and better clocks. And finally, we hope to see the kind of variation in the future.
thanks very much to the three panelists. It was an excellent session, and thanks to all of you for the exchanges. Thank you very much.